Okay, so today we will look at microscale fluid mechanics. Okay, so before we talk about microscale fluid mechanics, let us try to understand what a fluid is. Okay, a fluid is a substance that deforms continuously under the action of shear stress. Microscale fluid mechanics. So first try to understand what is a fluid. A fluid is a substance that deforms continuously under shear stress. Okay. So, a fluid is a substance that deforms continuously under the action of the shear stress. Okay. So, let us consider a block of solid and a force F is acting on it. So, when the force F acts on it, then it deforms, right, it deforms. So, this is we are talking about a solid. If you consider a liquid, when a force F acts, this is we are talking about a liquid, it when you apply a force F, it keeps on deforming, okay, as long as the force exists. Okay. So, in case of a liquid, if you apply a force F, then the solid is deformed, and when the force is removed, the shape is retained, the solid goes back to its original shape. Whereas in liquid, if you apply a force, then it deforms continuously as long as the force is existing, and when the force goes to 0, in liquid the shape does not go back to its original shape, it remains in that shape. Okay. And when force is again applied, it continues to deform. So, that is how the solids are different from liquids. Let us look at some of the properties of liquids. The different properties are kinematic properties. The kinematic properties are the properties of the flow, they may also depend on the fluid properties. Okay. So, some of the examples are velocity, acceleration and strain rate. So, we look at properties of fluids. So, we look at first kinematic properties. Kinematic properties are basically the properties of flow, and the examples are velocity, and acceleration and strain rate. So, these are kinematic properties. The second set of properties are the transport properties. The transport properties are properties of the fluid, okay, and these properties would affect how the fluid is transported, or in case of heat transfer how the heat is transported. So we talk about transport properties. These are properties of fluid, and the examples are viscosity, thermal diffusivity. Okay. Then we have thermodynamic properties. So thermodynamic properties will state the thermodynamic state of a fluid, okay, and the examples of thermodynamic properties are pressure, temperature and density. So the third set of properties are the thermodynamic properties. So thermodynamic properties are again properties of fluid, and the examples are pressure, temperature and density. Then we have miscellaneous properties. And the miscellaneous properties are the the properties that of the fluid that is because of the interaction between the fluid and the wall, or interaction between fluid and fluid, interaction between two fluids. So it is because of the interaction between fluid and wall, or fluid fluid interaction. Okay. So the examples of miscellaneous properties are surface tension and vapor pressure. Okay. So now let us look at three different states of matter, namely solid, liquid and gas. Okay. How their behaviors are different. So we look at three states of matter. So first let us look at liquid. The liquids have definite volume, they have definite shape, and they do not expand indefinitely. Okay. So the liquids have definite volume but do not have definite shape, because it takes the shape of the container and it does not expand continuously. Okay. Next we talk about gases. The gases, they have they do not have definite volume and they do not have definite shape, and they expand infinitely. So do not have definite volume or shape and expand continuously. And third is the solids, have definite volume and shape and they do not expand continuously. Okay. Now, if we look at the density of the solid, it is normally greater than 1000 kg per meter cube. Okay. So, the density, if you compare the densities, then the solid density is actually greater than 1000 kg per meter cube, and the liquid density is about 1000 kg per meter cube, and gas density is about 1 kg per meter cube. Okay. Now, if you look at the interaction, the molecular interaction, the molecules in the liquid, they are in constant state of interaction, they always interact and they move relative to each other. The molecules in the gas, they interact as and when they collide with each other briefly, whereas in solid the molecules are in a relatively fixed state and they can only move relative to each other when the temperature, their relative position is disturbed, for example by increasing the temperature. So, in solid molecules are in a fixed distribution and their molecular spacing is of the order of 0.3 nanometer. Okay. In liquid, the molecules interact continuously and their molecular spacing is also of the order of 0.3 nanometer. Now, in gases, the molecules interact only during collision and the molecular spacing is about 3 nanometer. Okay. So, that is how the intermolecular distribution is in liquid, solid and gases. Now, to analyze the behavior of fluids, we can do it in two ways. In one way, we can assume that they are a set of molecules. Okay, we can consider the fluid to be a distribution of molecules which are interacting with each other, or we can consider the fluid to be a continuous body. Okay, so where the point properties like pressure, density, velocity are defined throughout space. So, the fluid modeling can be done in two ways. One is they are set of interacting molecules or as continuum where point properties are defined throughout. Okay. So, first let us consider the fluid to be a as the set of molecules that continuously interact. So, here we will look at the molecular theory. Okay. So, we will talk about the molecular forces. Now, if we consider two molecules separated by distance r. So, this is molecule 1, this is molecule 2, their interaction is defined by Lennard-Jones potential. So, the interaction, the molecular interaction is defined by Lennard-Jones potential. Okay. So, the Lennard-Jones potential V12 is given by 4 epsilon into C12 into r over sigma to the power minus 12 minus D12 into r over sigma to the power minus 6. Okay. So, the first term is the repulsive term, this is the repulsion between two molecules, and the second term is the van der Waals attraction. Okay. Van der Waals attraction. The repulsion force can be determined using phenomenological models. Okay. So, this can be determined using phenomenological models. It cannot be derived, whereas the attraction force can be derived using different theory. There are different theories like Keesom theory, Debye theory or London theory. So, it can be used to derive the potential between two interacting non reacting molecules. Okay. So, that is given by the Lennard-Jones potential. Now, knowing the potential, we can determine the force that is acting between two molecules. So, we can determine the force F12, which is nothing but the differentiation of the potential dV12 over dr, which is given by 48 epsilon divided by sigma into C12 r over sigma minus 13 minus D12 r over sigma minus 7. Okay. So, here r is the separation distance between two molecules, epsilon is the energy scale. Okay. Epsilon is the energy scale and sigma is the length scale, and C12 and D12 they are specific to the molecules. Okay. And the characteristic time scale of interaction between the two molecules is given by tau. So, this is the characteristic time scale of interaction which is given by sigma into m over epsilon square root. So, this is the characteristic time scale of interaction where m is the mass of molecule. So, when the time scale is tau, then the Lennard-Jones potential can be used to find out the force between two molecules. Okay. So, let us see how the force and the potential vary with separation distance. As you can see here, as the separation distance increases, the force, if you look at the force, when r is very less, okay, which is of the order of sigma, and sigma for fluids is about 0.3 nanometer, then the force between the two molecules is repulsive in nature. Okay. And when the distance, separation distance increases, then the force, the repulsive force reduces, and slowly the force becomes attractive. Okay. So, about r equal to 0.9, the force starts to become attractive, and for r equal to 1.1 of sigma, and it becomes maximum. So, the attractive force become maximum, and as r is increased further, then the attraction force continues to reduce, but it never reaches 0. Okay. So, what we see here is when r is less than 0.3 nanometer, the interaction force is repulsive, and when r is greater than 0.3 nanometer, then the interaction force becomes attractive. Okay. So, that is what we observe from Lennard-Jones potential. Now, if we look at how does the intermolecular force vary for different phases, you can see for solids the intermolecular force is very strong, and the ratio of the thermal amplitude vibration to sigma, the characteristic length scale, is going to be very small, and you need quantum mechanics approach to handle that. Whereas in liquid the intermolecular forces are moderate, and the ratio of the thermal vibration amplitude to sigma is of the order of 1, and you would require quantum or classical mechanics to handle liquids. In case of gas, the intermolecular force is weak, and the ratio of thermal vibration amplitude to sigma is greater than 1, and you need classical approach to handle gases. So, now let us look at the continuum assumptions. So, we can assume that the fluid is continuum when there are a lot of molecules that present in a fluidic space. For example, if you consider a channel of 10 micron size and you have water present in the channel, there are about 30,000 molecules, water molecules present in the space. So it is almost packed with molecules, in which case we can consider the presence of liquid water in a 10 micron channel as continuum. We can treat it as continuum. So if we look at how we can define continuum in fluidics, here you see the variation of a point property density with the sample volume LQ. You can see that at smaller sample volume there is lot of variation in the density, in the point property. This is because when the sample volume is very small, let us say of the order of picoliter, okay, when you talk about a cube of size of the order of micron or nanometer, when V is very small, the fluid volume V is very small, let us say you have n number of molecules. Here we are saying that the fluid volume and the molecule volume are comparable, and if you increase the fluid volume by delta V very in a small increment, then the number of molecules still stays n, okay, because that increase in delta V is small compared to the volume of one additional molecule. So you are increasing volume from V to V plus delta V, whereas the number of molecules still stays n. So that would lead to sudden reduction in density, okay, because you are increasing volume without increasing the mass of the molecules. If you increase the volume further from V plus delta V to V plus 2 delta V, then suddenly maybe one molecule can be added into the volume. So suddenly you have n plus 1 number of molecules with equal increment in the volume. So there will be a sudden increase in the density, so that would lead to increase in the density. So for that reason, when the volume under consideration, okay, or the control volume is comparable to the size of the molecule, the volume of the molecule, then there are lot of molecular fluctuations, okay. So that leads to fluctuation in the point properties that we see in the left side of the plot. And when the sample volume is considerable, these variations are averaged out and you get almost constant value of density, which is called point value, okay. And when you talk about very large sample volumes, what happens is, if the volume is very large, then local fluctuations tend to occur. Let us say for example you have local heating of the flow, that will lead to change in the density at a particular location. So in that case also we cannot consider the flow to be continuous, the assumption that flow is continuous breaks down, okay. So next we look at the the distinction between continuum and molecular assumptions. So we look at distinction between continuum and molecular assumptions. Okay. So we look at nitrogen gas and liquid water. So as you see here, to describe the continuum assumption, we consider diatomic nitrogen and liquid water at standard conditions. So there are different properties that is shown here. One is the molecular diameter. The molecular diameter of nitrogen is about 0.3 nanometer, which is the same as the molecular diameter of water. The number density of nitrogen is 3 into 10 to the 5 per meter cube, and the number density of the liquid water is 2 into 10 to the power 28. The intermolecular spacing, the spacing between the molecules in case of nitrogen is 3 nanometer, whereas in case of liquid it is 0.4 nanometer, about 10 times less. The displacement distance, the distance the molecule travels between collisions is about 100 nanometer for gas, and it is about 0.001 nanometer for liquids. So, the liquids are in constant state of interaction. Okay. If you look at the molecular velocity for the gas, it is 500 meter per second, and for liquid it is about 1000 meter per second. Now let us differentiate between the molecular and continuous behavior by considering two fluids. One is liquid water and the second one is diatomic nitrogen. For statistical confidence we will consider about 10 to the power 4 number of molecules, so that we have enough molecules to know their behavior. Okay. So we will consider nitrogen gas and liquid water, and we would consider 10 to the power 4 molecules for statistical confidence. Now first, to have the point properties to be continuous, we would determine what should be the point volume. Okay, what should be the volume of the space, so that we can consider either the liquid to be continuous and the gas to be continuous. To consider the gas to be continuous, the length scale of the gas has to be, so 10 to the power 4 molecules we are considering, and the molecular density of the gas is 3 into 10 to the power minus 25 per meter cube. Okay. So take the cube root, we get 70 nanometer. So if we consider a gas cube that has dimension 70 nanometer each side, then we can expect that the point properties will be continuous. For liquid, for water, it will be 10 to the power 4 divided by the number density is 3 into 10 to the power minus 28 per meter cube, and if you determine that, it will be about 8 nanometer. So if you have liquid water in a point volume that has the cubic size of each side 8 nanometer, then we can expect that the liquid water is still continuous. Now next we will determine if we talk about the transport properties. Transport properties to be continuous, we expect that, for example, viscosity is continuous, then we say that the volume of the cube would be about 10 times the distance of travel of the molecule. Okay. So in that case the L gas would be 10 times the distance the gas molecule would travel, which is about 100 nanometer is the separation distance. So 10 into 100 nanometer, so which is about 10 to the power minus 6 meter. For liquid water, for water the molecules are in constant state of interaction. okay. So in that case the separation distance will not be a good parameter to establish its length scale, okay, at which it will be continuum, whereas the size of the molecules, okay, would be a good parameter to establish whether the liquid water is going to be continuous. So same way we consider that it is 10 times the size of the molecule, which is 1/3 into 10 to the power minus 28, sorry, this would be plus 28 not minus 28. So these are number of molecules, so these are all plus, minus cube root, so which will be about 8 nanometer, okay. So what do we see here? We see here that for gas to be continuous the length scale of the flow has to be at least 1 micron, okay, and the length scale of the liquid has to be at least about 8 nanometer or 10 nanometer, okay. So for continuum behavior gas has to be 1 micron and water is about 10 nanometer. So this is very important to understand in which case we are going to expect continuum behavior. If you are talking about liquid flow of water through two parallel plates and the separation distance is less than 10 nanometer, then we can consider the flow to be in molecular regime. We cannot apply the continuum governing equations to solve for the flow, whereas in case of gas flow, if the separation distance is above 1 micron, then only we would expect that the continuum behavior is expected, okay. So that is very important to understand. So having said that, let us look at the continuum fluid mechanics. As you know that in most microscale flow situations the separation distance or the length scale of the flow is going to be well above 10 nanometer. We can say that for most of the liquid flows the flow can be treated as continuum, okay. So with that let us talk about the governing equations for the fluid flow at microscale. Governing equations, so the namely mass. So the mass conservation equation can be written as follows, is del rho over del T plus del over del Xi into rho Ui is 0, and the first term is the rate of change of density, the second term is the rate of influx or outflux of mass, so rate of inflow of mass. Next we can write the momentum equation, which is del over del T into rho Ui plus del over del Xj into rho Uj Ui equal to rho Fi plus del over del Xj into tau Ji. So this is the rate of momentum increase, this is the rate of momentum flux, this is the body force and this is the total stress, and this total stress will have the pressure component plus the viscous stress. We can write the energy equation del over del T into rho E plus del over del xi to rho ui E equal to minus P into del ui over del xi plus tau Ji into del ui over del xj plus del qi over del xi. So, this is the rate of trough, rate of increase of energy, this is convection of energy, this is the pressure work, this is the viscous work, and this is the heat flow. So, if you look at here, we have 5 equations and we have 17 unknowns. Okay. So, those unknowns are, we have ui 3, we have pressure, we have temperature, and we have the stress tensor. We have 9 components, and then we have the qy 3 components. So, we have totally 17 unknowns and 5 equations. So, to solve we require the constitutive relations, constitutive relations. So, that means we need the relation between the stress and velocity field, we need relation between heat flux and temperature field, and we need to express thermodynamic properties. Okay. So, this is what we need to solve the 5 equations, the mass, momentum and energy. Now, there are the CFD codes available which can solve these equations, and in some special cases where the physics of the problem can be simplified and these equations can be simplified to a form which can be solved analytically, we can obtain the solutions also. So, with that, first let us try to look at gas flows, okay, then we will move on to liquid flows. So, first we try to look at gas flows. Okay. So, the gas flows can be described by the kinetic theory of gases, and in order to apply the kinetic theory of gases, one requirement is that the molecules of the gases should move in a straight line between the collisions. So, that is the assumption that we are making. Okay. So, under that assumption we are able to apply the kinetic theory of gases, the kinetic theory of gases, okay, where we first look at the equation of state which is P equal to n k T, or is also written as rho r T, where n is the number density, how many molecules we have per unit volume. So, number density is meter per meter cube, k is the Boltzmann constant, and T is the temperature, R is the specific gas constant, and rho is the density, okay. And this Boltzmann constant K has a value which is 1.328 into 10 to the power minus 23 joule per Kelvin. The specific gas constant R can be written as universal gas constant divided by the molecular mass. So, this is universal gas constant and this is the molecular mass. Now, at standard conditions, standard conditions meaning the temperature is 273.15 and the pressure is 101.325 kilopascal, we would have the number density N0 to be 2.7 into 10 to the power 25 per meter cube, okay. So, at standard conditions we have this many number of molecules per meter cube. So, we can find the mean molecular spacing. So, the mean molecular spacing will be the cube root of that, right. So, delta will be N0 to the power 1/3, which will be equal to 3.3 into 10 to the power minus 9 meter. So, the mean molecular spacing under standard condition is about 3 nanometer, okay. And if you can compare the spacing between the molecules with the diameter of the molecule, and if the diameter of the molecule to the spacing ratio is going to be very small, then the gas is called dilute gas, okay. So, if D is the molecule dia and the ratio of delta to D, for example, in case of nitrogen is going to be 3.3 into 10 to the power minus 9. So, diameter will be about 3 into 10 to the power minus 10, okay. So, this will be about 10, okay, which is greater than 1. So, if delta by D is greater than 1, then it is called a dilute gas, okay. So, in dilute gases you would have only 2 molecules colliding with each other at one time, you know, many molecules or more than 2 molecules colliding with each other is not possible, okay. So, next we look at you know 3 different important parameters in the gas flows. One is the you know the lambda, which is called the mean free path. So, mean free path, we look at 3 different parameters here. One is mean free path, which is lambda. We will also look at mean square molecular speed, which is denoted by Cs star, and we will also look at speed of sound, which is Cs. Okay. So, the mean free path lambda can be, so the mean free path is the distance that a molecule will travel between two successive collisions. Okay. So, lambda can be expressed as follows: lambda is given by square root of 2 into pi into d square n to the power minus 1. Okay. So, this is the expression for the mean free path. Okay. So, the molecular speed Cs, mean square molecular speed, can be written as 3 r into t, and the speed of sound can be written as square root of k r into t. Okay. So, here the d is dia of molecule and n is the number density, okay, how many molecules per meter cube, r is the specific gas constant, and T is the temperature. The K here is the specific, sorry, yeah, this is specific gas constant, and K is the specific heat ratio, that is Cp over Cv. Okay. And viscosity can be written as, so nu will be half into lambda into C bar, okay, which is the speed of the mean molecular speed. Okay, so this is actually C bar, not Cs. This is denoted by C bar. So there is a correction here also. So here we write this C bar. Okay. So this is how the viscosity can be, using this expression, the viscosity can be related to temperature and pressure, as the mean free path lambda is a function of pressure, and C bar, the mean square molecular velocity, is a function of temperature. Okay. Next, let us look at some of the dimensionless parameters in gas flows. We will look at Knudsen number, we will look at Mach number, and we will look at Reynolds number, and we will see how they are related. Okay. So let us look at dimensionless parameters in gas flows. Okay. First is the Mach number, denoted by Ma, then you have Knudsen number, Knudsen Knudsen number. Okay. Then you have Knudsen number is denoted by Kn, and then you have the Reynolds number. Re. Okay. So first let us talk about Mach number, Ma. Mach number is the velocity of a fluid, ratio of the velocity of a fluid to the velocity of sound in a medium. Okay. So Ma is U divided by Cs, and it is also referred to as the ratio between the inertia force to the elastic force. Okay. So, ratio between inertia to elastic. Okay. And depending on the Mach number we can categorize the flow. For the flows where the Mach number is greater than 1, it is known as supersonic flow. When they are of the order of 1, they are sonic flows, and when Mach number is less than 1, they are subsonic flows. So, Mach number greater than 1, supersonic flow, equal to 1, sonic flow, and less than 1 is subsonic flow. Okay. So, we can say, let us say for example gas is flowing through a channel, and we know that gas is compressible, but within the channel if there is no variation in the density, okay, we can consider the flow to be incompressible. Okay, that is a very important concept to understand in fluid mechanics or in gas dynamics. The fluid could be compressible, but if there is no change in the density inside the device, the density is not varying, we can consider the flow to be incompressible. Okay, so fluid can be compressible, let us say gas, but if the Mach number is less than 0.3, then we can consider flow to be incompressible. Okay. So, let us consider a flow through two parallel plates, and let us say gas is flowing, and density here is rho 0 and is continuously staying rho 0 till this point. And so, in that case even if gas is compressible, the flow could be considered as incompressible, and most likely the Mach number, if the Mach number is less than 0.3, we can still go ahead and use the governing equations that is applicable to incompressible flow to this situation, provided few other conditions are satisfied. For example, in this case if we have let us say here somewhere there is local heating of the flow, if you have local heating, then around here, around this region, the density may be rho 0 dash, which is different than rho 0. So, in that situation if you are analyzing this domain, okay, we cannot say that the flow is incompressible. Okay. So, in addition to satisfying the condition that Mach number is less than 0.3, there should not be any local heating of the flow. There are other cases, for example if there is a fluid, there is a gas flowing through very thin parallel plates and the viscosity is considerable, okay, then there will be viscous heat generation and there will be heat loss, okay, there will be self heating of the gas. So, in that case also we cannot consider flow to be incompressible. So, normally if Mach number less than 0.3 we consider incompressible flow, provided there is no local heating, no self heating of the flow of the flow. Okay. So, that is the condition, even if the Mach number is less than 0.3 there should not be any local heating, there should not be any viscous heat generation. So, with that we move on to talk about what is the Knudsen number. So we will talk about Knudsen number, which is denoted by Kn. So Knudsen number is defined as the ratio between the molecular length scale, okay, the mean free path lambda and the length scale of the flow, okay. So Knudsen number is lambda over L. So that is lambda is the mean free path and L is the length scale of flow. Now depending on the value of the Knudsen number, we can categorize how rarefied the flow is, okay. So there are different ranges of Knudsen number we can come up with. If Knudsen number is less than 0.001, then we can treat the flow to be continuous. We can apply the Navier-Stokes equation and the boundary conditions, no slip boundary condition. If the value of Knudsen number is between 0.1 to 0.001, then we can still apply Navier-Stokes equation, but with slip boundary condition, okay. And if Knudsen number is between 0.1 to 10, then we are in the transitional regime where we need to modify the Navier-Stokes equation in order to use it. And if the Knudsen number is greater than 10, we get into molecular regime. Knudsen number is less than 0.001, you can say that Navier-Stokes equation applied with no slip, okay, and 0.001 if Knudsen number is between 0.001 to 0.1, then Knudsen equation is used with slip boundary condition, and if Knudsen number is between 0.1 to 10, then we are in the transitional regime, okay, where Navier-Stokes equation modified, and if Knudsen number is greater than 10, then free molecular flow, okay. So next we talk about Reynolds number. Reynolds number is the ratio of the inertia to viscous force. Reynolds number is denoted by Re, which is rho u d over mu, and depending on the value of the Reynolds number, we can categorize the flow. If Reynolds number is less than 1500, we can say is laminar. Reynolds number greater than 1500, you can say is going to be turbulent, although at micro scale this is debatable, okay. So which we will be discussing later on. So here this is density, this is density, this is length scale, and this is viscosity, and u is the velocity, okay. So now we can relate the Mach number relation between Mach number, Knudsen number and Reynolds number. So the relation is going to be this: the Knudsen number will be equal to K into pi by 2 square root into Mach number divided by Reynolds number. Okay. And we stop here.